Hello, good morning. I am Dr. Srinivasa, working as an assistant professor of physics in IDSG Government College, Chikmagalur. In this video, I am going to explain some concept of natural radioactivity, which is a chapter in a 3rd BSc 6M paper 8 physics, and the paper name is Nuclear and Particle Physics, subject code SSF 611. This is session number 6 video. In this video, I am going to explain what is radioactive dating and also types of radioactive dating, and using radioactive dating how to measure the age of the archaeological samples and also age of the earth and rocks. First of all, what is radioactive dating? The presence of radioactive substances in rocks and earth crust provide useful information about the age of the rock, fossils and earth. The presence of radioactive substances like uranium, radium, potassium 40, carbon 14, etc. in rocks and earth crust provide useful information about the age of the rock, fossils and earth. The method of estimating age of archaeological samples such as rock, fossils and earth is called radioactive dating. The method of estimating age of archaeological sample is using the radioactive substances is called radioactive dating. There are two types of radioactive dating. First one is radioactive carbon dating. What is radioactive carbon dating? How it is used to measure the age of the archaeological samples such as age of the wood, plants and also dead animals. The method of estimation of age of plants and animals after death by measuring the activity of carbon 14 present in them is called radioactive carbon dating. Here we know that radioactive isotopes of carbon. So here carbon 14 is a radioactive isotope. So the method of estimation of the age of the plants and animals after death by measuring the activity of carbon 14 present in them is called radioactive carbon dating. So dear students, we know that carbon 14 is a radioactive isotope of carbon which is produced continuously in the upper atmosphere by the action of cosmic rays on the nitrogen which is in the atmosphere. We know that the half-life of carbon 14 is 5600 years. The carbon 14 decays with emission of beta rays. So the carbon 14 continuously decays with the emission of beta rays. The formation and decay of carbon 14 can be shown by the reaction as, so in the atmosphere nitrogen is present and this is a neutron. That means cosmic rays consists of neutrons. When neutrons bombard with the nitrogen gives rise to the carbon 14 isotope and also protons, hydrogen, and in turn this cis carbon 14 radioactive isotopes decays with a beta particle forming 7 nitrogen 14. That means in the atmosphere nitrogen is converted into carbon 14 isotope and carbon 14 decays to form a nitrogen continuously. So the concentration of carbon 14 in atmosphere is constant with the time. Thus production and decay of carbon 14 has reached the equilibrium state. Due to conversion of nitrogen into carbon 14 and carbon 14 into nitrogen, they attain a equilibrium state in the atmosphere. How? By measuring the activity of carbon 14, we can measure the age of the archaeological sample. The living plants and animals absorb carbon 14 along with carbon dioxide. The living plants and animals absorb carbon 14 along with carbon dioxide from the atmosphere in the form of food for their growth. When the plant or animal dies, the intake of carbon 14 stops. When the plant or animal dies, the intake of carbon 14 stops, and carbon 14 already present in them at the time of death disintegrate exponentially with the emission of beta particles. That means the activity of carbon 14 goes on decreases when they stop taking intake of carbon. The age of plants and animals can be estimated by measuring the activity of carbon 14 in the given matter and also in the living animals and plants. Let A0 and AT be the activity of carbon 14 in living and dead matter respectively. A0 and AT be the activity of carbon 14 in living and dead matter respectively. Then we already know that activity can be represented as AT is equal to A0 into e to the power of minus lambda T, where lambda is the decay constant. So by dividing AT by A0 is equal to e to the power of minus lambda T, or taking the reciprocal, A0 by AT is equal to e to the power of lambda T, or take log on both sides, we get lambda T is equal to log E A0 by AT. So by using the common logarithm, by multiplying with 2.303, we get T is equal to 2.303 log 10 8 naught by 80 over lambda. So using this equation for time or age of the archaeological sample can be calculated using this formula. T is equal to 2.303 log base 10 A0 by 80 over lambda. So from the, we know that half life of carbon 14 as 5600 years. By knowing the half life of carbon 14, we can calculate the value of decay constant by using the formula lambda is equal to 0.693 over T off. So from this formula we can calculate the value of decay constant, and by measuring the activity of carbon 14 in living and dead sample as A0 and AT, we can calculate the age of the archaeological sample or dead animal or plant. The second one is age of the earth or uranium dating. So by measuring the activity of the uranium in the samples of the planets like Earth, we can measure the age of the Earth or planets. The ages of Earth and Moon, rocks and of meteorites are measured by the decay of long-lived radioactive isotopes of elements that occur naturally in rocks and minerals, and the decay with half-life of 700 million to more than 100 billion years to stabilized isotopes of other elements. The ages of the earth and moon rocks and of meteorites are measured by the decay of long-lived radioactive isotopes of elements that occur naturally in rocks and minerals, and the decay with half-lives of 700 million to more than 100 billion years to stable isotopes of other elements. The two isotopes, that is uranium 238 and uranium 235 of uranium, were assumed to be produced in equal proportion when Earth was formed. It was assumed that uranium 238 and uranium 235 are assumed to produced in equal proportion when Earth was formed. The measurement of present proportion of these two isotopes in a sample helps to estimate the age of the rock or Earth or any other planet. The measurement of present proportion of these two isotopes in a sample helps to estimate the age of the rock or Earth. Using the mathematical formula, we can calculate the age of the Earth by uranium dating. Let N1 and N2 be the number of atoms present in uranium 238 and uranium 235 respectively. N1 and N2 be the number of atoms present in uranium 238 and uranium 235 respectively, and lambda 1 and lambda 2 be their decay constants. Lambda 1 is the decay constant of uranium 238 and lambda 2 is the decay constant of uranium 235. Let N naught be their initial number of atoms during the formation of the Earth. In both cases, N naught be their initial number of atoms during the formation of the Earth, which is same for both isotopes. If T is the age of the Earth, then we know that number of atoms present in the radioactive sample at any instant of time is given by N is equal to N naught e to the power of minus lambda T. So for uranium 238 it is N1 is equal to N naught e to the power of minus lambda 1 T, and for uranium 235 N2 is equal to N naught e to the power of minus e to the power of lambda 2 T. So divide these two equations. We will get N1 by N2 is equal to e to the power of lambda 2 minus lambda 1 into T, or take log on both sides. We get lambda 2 minus lambda 1 into T is equal to log of N1 by N2. So by taking common logarithm and also simplification, after simplification, so the time, age of the Earth can be calculated as T is equal to 2.303 log of N1 by N2 divided by lambda 2 minus lambda 1. So where N1 is the number of atoms present in the uranium 238 sample and N2 is the number of atoms present in uranium 235 sample at that instant of time, and lambda 1 and lambda 2 their decay constant. By knowing half-life period of uranium 238 and uranium 235, we can calculate the value of lambda 1 and lambda 2, and by knowing the number of atoms present in the uranium 238 and uranium 235 at any instant of time, we can calculate the age of the Earth using uranium dating. The present ratio of uranium 238 and uranium 235 in a sample is found to be 140:1, and their half-lives are 4.5 into 10 power 9 years and 7.07 into 10 power 8 years. So lambda 1, using the equation for decay constant, lambda 1 is equal to 0.693 over half-life of uranium 238, that is 0.693 over 4.5 into 10 power 9, and lambda 2 is equal to 0.693 over half-life period of uranium 235, that is 7.07 into 10 power 8. Substituting the values of lambda 1 and lambda 2 in this equation and ratio of uranium 238 to uranium 235 as 140:1, and after simplification we'll get the age of the Earth as T is equal to 6000 into 10 power 5 years or 6000 million years. Using the present ratio of uranium 238 and uranium 235, by knowing using the values of half-lives and calculating decay constants, and after substitution in this equation, we can estimate the age of the earth as 6,000 million years. The third one is age of rock. In 1913, Jolly and Rutherford suggest that if igneous rock formed as a result of prehistoric volcanic eruption contained a small amount of uranium, it would steadily decay, leaving less uranium and depositing more stable lead-206 isotope. By measuring the ratio of uranium to lead in rock samples, a rather exact time can be determined for the origin of the geological deposits. Rutherford and Jolly in 1913 suggested that if igneous rock formed as a result of prehistoric volcanic eruption contained a small amount of uranium, it would steadily decay by emitting the radioactive rays, leaving less uranium. As it decays, it becomes less and depositing more stable lead-206 isotope. By measuring the ratio of uranium to lead in rock samples, a rather exact time can be determined for the origin of the geological deposits. Uranium dating measures times of the earth around millions of years, as I already explained in the last slide. So these are the references, reference books I have used for making my PPT as well as video. Thank you for watching. Thank you once again.